So this is kind of what I did in class, where we see that these would kind of be, and I guess I'd unwind all the way to the front and get this. So this one, the tree would be rooted at A, then it would go to B, then B would go to C, which would go to D, which would go to E, which would go to F, then it would also go to I, then it would go to G. We'd unwind all the way back up, and A would also go to H. So the idea was that you can create spanning trees from this graph depending on how you choose your neighbors and how you what you choose as your root. What did people think? What were the best routes to choose? Or I guess in some ways the worst routes to choose, because you typically don't want a tall tree. But assuming we did want to get as tall a tree as possible, what were the routes people chose? Yeah, so again, if we start with H, we see that we can actually have everything just go down one branch. Like that. So then the tree would just look like it would be H at the top. H, then A, then B, then C, then D. Let me go the other way just so I have room. Then G, then I, then E, then F. So we did just have this one long tree that basically just looks like a linked list. Similarly, we could do this exact route backwards from F. Does that make sense, Jacob? Yeah. Yeah, that's fine if you only got H. It was, I guess, kind of noticing that you wanted one that kind of was out on its own. So it only, when you did a depth first search from that node, and you also wanted to make sure that you could actually have a path from that node and reach all the other ones without having to trace back at all. And that's why like something like C isn't good, because C, if you go this way, you're going to have to actually come back to C before going out the other way. So C is going to have two subtrees, one with kind of B, A, H, and another one with all these on the other side. So the idea was kind of seeing based on the structure of this graph and strategically thinking, okay, from this node, I can actually reach all the other nodes on a single path. So I guess depending on how you represent your nodes, and maybe now's a decent time to, yeah, it is up to you, as Leo's saying. But again, if we look at what we did last day on this front page, when we kind of talked about this, I guess if you're representing your graph as a matrix, again, you'll probably go through a row in this order. Say, this is my first neighbor, this is my second neighbor, this is my third neighbor. So again, it depends on how you organize your rows. Whereas here, same thing, when we have a linked list, we can go to the front of the list, the back of the list. And again, are you organizing the things in the linked list alphabetically, or are you just adding them arbitrarily? So it kind of depends on if you have a strategy in place for, I guess, first of all, how you're implementing how you're representing the graph as data in your program. Is it with a matrix? Is it with a list? And if so, which one? How are you determining the neighbors? How are you progressing through that list of neighbors? In an array, you typically go just from index 0 to the end, so you probably would get them in order, alphabetical order. But here you might be adding things to the front or adding things to the back as you want to add things to your linked list of neighbors. And in that case, it kind of depends on how you're adding things to your adjacency list. Does that make sense? So before I actually jump into this worksheet again, I do want to talk about the assignment. So I've got assignment 6. I think it should be automatically released to everyone at 10:30 a.m. today. So as soon as the lecture opens, and the resources right now, A6, again, it's hidden until 10:30 a.m. So as soon as this lecture ends, you should be able to access. I know some people are wanting to get started. So again, how the assignment works is that there are a bunch of theoretical questions. Again, we're working with some graphs, some adjacency lists, some adjacency matrices. Then again, there's doing some traversals, and then there's more of a proof theoretical question. And then the last part's programming. And what I want to talk about is, I guess, what images actually look like. So I'm not sure how much everyone in this class knows about images, but again, if I zoom in on an image really, as far as I can go, what all images really are again, different kind of pixels. So again, if I zoom in on this image really quick and I can kind of draw things, and it's really just a grid of pixels. And again, when I zoom out, that image is actually going to look really small, and it's actually going to look like a curve, as opposed to when I zoom in really quickly, it's not a curve at all. And each of these pixels in this grid, we see that if I go to the bottom right corner, down at my screen, down on the bottom left screen, it's kind of saying what pixel I'm currently at. If I go back to my mouse. Oh no, sorry, this is the total size. And this is my current location. So here, if I go up to the top left, I'm at 0, 0, or 0, 0, 0, 0, 1. And if I go right, we see that x coordinate is increasing. As I go down, the y coordinate's going to increase. And again, each one of these pixels is, can I choose? Is we can represent it as an RGB color of 3 components, red, green, and blue. So something that's fully red, 255 red, and 0 of the other colors, we see is really deep red. Whereas something that's has no colors, just black, if it's full of colors, it's should be white. And again, if it's only kind of the blue, it's just going to be all blue. And then we can kind of get mixes of colors by combining these in different ways. So all green and all blue gets this color here. And I can move this around here and see the different colors. So this pink is again mostly red, but it's also got some blue and some green. So all the different colors here can be represented by red, green, and blue values between 0 and 255. And then when we're coloring, all we are is we're just changing the pixel value in this image to one of these colors represented by these RGB values. So the last thing I want to talk about is actually flood fill. So flood fill is when you choose a color and then you click on your graph and it's going to fill everything, all vertices, or I guess all pixels in the image of the same color are, so everything that's white bordered by these other colors to that same color. And I can do this in different regions, I guess. And if this red went a little bit further down, it wouldn't fill it all the way around. So now I can kind of fill different regions, different colors here. And why I'm talking about this is because for the programming part of the assignment, you're going to be doing some stuff with images. And again, here's an image of a house that I drew. And again, if I kind of put in a grid to see just what the different pixels in the image are, again, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, we could think about this as a grid of pixels. And we could also represent this as a graph. So in the graph representation, what we're going to have here is that every one of these pixels is represented as a vertex. And the edges just connect the adjacent pixels in the corresponding image. But what you'll also see is that there aren't connections between different colors. So there's no connections here. So what this does is this graph has a few different sets of connected vertices, and it's all the adjacent vertices of the same color. So what happens is if we want to actually do something like that flood fill, what's going to happen is if I say, let's color everything red starting here, we know in the image what that'll do is that'll color everything red. What that should do in your thing is it should say, I'm going to color all of the connected vertices to this one red. Does that make sense? So every reachable vertex, and again, because I've said that how I've constructed this graph from an image for you is each vertex is connected to other vertices within the same color. And so again, all these blue ones are connected. We see here, all these blue ones are connected. So if I click to flood fill one of these blue ones, it would recolor all of these. Does this make sense so far? Cool. So I'll show you what you're going to be doing. So you're going to run the tester, and if you try and run it like this, it'll say you should put the Java 86 tester and then an image. So I'm going to instead say Java smile. So we've got this little smiley face here. And what I can do is I can choose a color to do my flood fill. And then what I can do is I can choose to do DFS or BFS. We haven't seen breadth first search yet, but we'll see it in the videos for tomorrow. And it's just going to fill this up. So we know the depth first search is going to, again, keep going as deep as it can, and then it'll backtrack once it has no neighbors. So again, it's always going to go as far down each path as it can, and then backtrack. Whereas what we'll see with breadth first search, which we'll see in the videos for tomorrow, it actually pulses out from that center point. It doesn't do a long path as far down a path as it can. It pulses out from a given start point. So you'll see that these flood fills work quite differently. So one fans out, one always does a line as deep as it can, and then it'll backtrack back to the last one that had uncolored neighbors. So I've provided a couple different files for you, CSC small. And you can see how these work. You will see that for some of these, when I zoom in so much, there's a couple artifacts that you don't really have to worry about. I'll show you what I mean in a second. There'll be some kind of white little dots sometimes that show up. So like you can see some white little lines here that sometimes show up. I wouldn't worry about those. It's just in the Java animation. The Java program I've written isn't super great at doing images. It has some little artifacts there that show up momentarily. But again, as you can see, this algorithm, the breadth first search, it's doing one line at a time and coloring that line and up until it finds no other neighbors. And then it's going to backtrack, unwind back to the last one that did have a neighbor. Again, showing a breadth first search, which is different, is just going to pulse out. Yeah, so you're going to be writing the breadth first search and the depth first search flood fill algorithms, which is essentially just a graph traversal, but instead of when you visit a node, which is you're just going to color that node in a new color. Does that make sense? And I think I also just put in the maze I made for the videos last night as one of them. So again, with this maze, what we can see is if I do a depth first search, it's just actually going to go through and actually solve the maze. And it's going to keep going because I didn't tell it to stop at the finish, but it would have kind of been able to solve the maze. Whereas the breadth first search will fan out and it'll try every path to, like when it gets this fork here, it'll go in each direction from each fork at the same time. So again, it will solve a maze, but it's maybe if you don't find yourself, like if you kind of envision how this works, it's going to kind of go one step down one path, then one step down the other path, and one step down the other path, then two steps down the first path, two steps down the second path, two steps down the third path, which isn't maybe super efficient because it maybe makes more sense to go right down to a dead end and backtrack, then right down to another dead end and backtrack. So again, these algorithms can be used in different ways and are better at doing different types of things. So again, we haven't seen breadth first search. So you should be able to complete most of the assignment before tomorrow's videos. Just the last part and the last the coding part for breadth first search will be maybe difficult until I release the videos later today. But again, there are all the other kind of the 3 written questions before that we've covered already up to this point, or we will cover in today's lecture. Any questions? No, we're not really going to work on the coding because there are, you can actually, we will talk about the algorithm today in today's lecture, but we're not going to actually work on coding it because you will, I think like just using the pseudocode from the slides should hopefully be enough. You don't, no, you don't need to. There's just a one proof question. And it is actually a proof technique that we've used previously this term. I didn't actually say which one to use. I'm allowing you to choose how you want to do it. I mean, you're welcome to just kind of provide images or kind of stuff like that if you want, or there is one specific proof technique that I use to solve mine, but I'm giving you a little bit of flexibility there. So oh yeah, wait, I already have this open somewhere. So we need to finish off this table really quick, and I'd like to go to the next page as soon as possible. We do still have half an hour. Hopefully we can get it all done. So again, the space required for, oh, let me just move my, yeah, okay. I'm gonna move my tablet over top of my keyboard. So the space required for the matrix, I think we did this last day, some of this at least. And we know that this is just gonna be n squared because again, we're doing an n by n matrix up here, where again, remember that n is the number of vertices, m is the number of edges. Whereas the space required to do an adjacency list is going to be O of n plus m. It's always going to be, the amount of space required is going to be, we're going to have to allocate an array or something to keep track of our vertices. And then we're going to allocate nodes depending on the number of edges. So this is going to be, we're going to have to allocate space for n vertices and then in our array, and then m nodes in each one of those linked lists. So to get the list of vertices, again, in our array, in both the array matrix and the vertex list, again, we can just say, let's get this list of vertices. We can just loop through that array, and we can get that quite easily. But in terms of getting the list of edges, for the matrix, we actually have to go through all the different rows for each one of our edges, or yeah, each one of our vertices, to see what other vertices they're connected to see which values are 1 in each of these rows. So we're going to have to go through all n columns of all n rows. So it's going to be n squared. Whereas to get all the edges here, we're going to have to, again, look at each different vertex, which is O of n, and then go down and traverse through the linked list associated with each one of those vertexes. So it's going to be the same. These are the same as we see, because that's kind of how you're representing. You're either representing them in this matrix or in this linked list. Now is when we start seeing things get quite a bit different. So if we want to know, is one vertex adjacent to another? So again, I'm looking at vertex A, and we want to say, hey, is vertex C connected to A? In the adjacency matrix, we can just say, okay, is the slot at C a 1 or not? So again, we can directly access that thing at the given index of an array or a 2D array, and just say, is this value a 0 or 1? really quickly and easily. Why don't I actually put a little bit of an explanation here? This is an array lookup. It's just a quick and easy array lookup. Okay. In a, what about, so in the adjacency list, again, if I want to say is A connected to C, I got to go to A, and then I'm going to have to go through this whole linked list. Or I could say, let's go to C's list and see if A is in it. So again, if these are connected, I can either go to one list or the other and have to go through that whole linked list and see if C is found in A's list or A is found in C's list. Either one will work in an undirected graph. So what this is going to be is this is going to be O, and it's going to be the min of, I guess if we want to be efficient, we could say which one of these linked lists is smaller. It's going to be the minimum of the degree of A, or I guess, I don't know, I could say X or Y, or U and V. Degree of U or the degree of V. So I can say which one of these lists, the degree of a vertex, which one has the most children. I'm just going to choose the smallest one and then just go through this list and see if C is in there. So we have enough information to know which one of these lists is smaller, and then we can just choose to search through that. But again, it's going to be longer. It's not just going to be constant time. It's going to be depending on the number of edges, I guess how well connected the graph actually is. Does that make sense? How do we know in advance which? Typically, again, you might in your vertex list, you might either have a degree attribute for each one of these vertices, like it's in the vertex class, it might have a degree. Or again, if each vertex has an associated linked list, that linked list probably has classic linked list operations like add front, add back, size. So you could know, okay, is the size of A or the size of C smaller? If A is smaller, then I'm going to search through this linked list and see if C is there to know if these two vertices are adjacent. Does that make sense, Andy? Yeah, cool. So for these next ones, what I might do is kind of box them, because this kind of, again, is quite dependent on implementation. I mean, obviously all this stuff is, but these ones in particular, because what I'm going to say is to insert a vertex, what we might do is we might create a massive adjacency matrix that allows us originally to add more vertexes easily. So again, we might have a whole bunch of wasted space here initially, where I can eventually add nodes G, F, H, etc. And then all I do is have to start filling out a new row. But that's probably, I mean, we probably won't want to do that because it wastes so much space. So what we're probably going to have to do is make a new matrix that's, instead of n by n, it's going to be n plus 1 by n plus 1. So we can add that new vertex, and then we're going to have to copy it all over again and add this new row and column. So, I mean, the reallocation is going to be expensive for the adjacency matrix. I'm not going to have enough room for it, so I'm going to get smaller again. So to reallocate and copy, that's going to make it O of n squared. But once that's done, to insert a new, I guess, to insert the actual to to insert the values isn't necessarily bad. And again, why I've got this with remove vertex, again, if we want to say now remove this vertex E, what I guess we could kind of do is just set this in our array, set that value to null. So we could do that in O of 1, set to null, but we probably wouldn't want to do that. We'd probably, again, it depends on what we want to do. We might instead have to allocate a new array that's got one less row and one less column, and then copy all the values out there. So again, it depends if we're going to do that reallocate and copy, or which is going to take a long time, or if we just want to setting a new value in the matrix is quick and easy, or setting it to 1 or setting it to 0, setting it to null. But it's the reallocation and copying which takes a lot of time. Similarly, with the adjacency list, again, if we have to allocate a new array, we might have to actually copy all this stuff over. So I'll kind of say this is similar. So it's similar and mostly dominated by the reallocation. So that's the big bottleneck, is actually the reallocation, as opposed to the runtime of the actual algorithm. So again, now to insert and remove an edge in an adjacency matrix is really quickly. If we want to say, oh, I want to add an edge between A and C, or sorry, A and D, I could just say, boom, let's make this a 1 and this a 1, and I'm done. So that's really quick and easy. On the other hand, if I wanted to remove an edge, I could just say, okay, I want to remove the edge between A and B. I'm just going to make B and BA equal to 0. So those are really quick and easy. It's just, again, an array update, which we know we can do really quickly. To insert an edge here, so if I want to do A to D here, again, I can just say like A dot, the linked list associated with A, like insert front or insert back, and I can do that in constant time. Similarly, I can do same with D. I can say insert front or insert back my A onto this. As soon as I'm not, again, as Leo, I think was it Leo or Jacob at the beginning of class that asked about how our neighbors are organized. Oh, Jacob asked, Leo answered. Again, assuming we're not having to sort our adjacency list in any way, we can do this really quickly in O of 1 time as well. Just an insert front or insert back to a linked list. This is the same here, Jacob. It's the reallocation is going to take all the time. Where I guess, I mean, it will be it'll be, well, we're basically gonna have to create a whole new thing. So it's gonna be, you're gonna have to create a whole new you're kind of having to reallocate and copy everything from scratch. So so again, to remove a list, we're going to actually have to remove it from, like, if I wanted to disconnect A and C, I'm going to have to remove it from here and remove it from here. So this is going to be, and what I'm going to say is, I'm going to say it's based on the degree of the vertexes. And it's going to be, I guess, also the degree of dominated by the maximum of the two, because we're going to have to remove it from both. Or I guess I could just say, because again, I'm going to, even if A's only got 1, that's going to be quick and easy. So the big O time is going to be dominated by the one that's the longer one, because we might have to actually search through that whole linked list before we find the one we want to remove. And the last thing, if I want to know what are the edges incident to a vertex, again, what are the edges that A has? It's got these two edges. I just have to go along this row. So it's going to be O of n. Whereas here, it's going to be the degree of that vertex. Again, if I want to know how many edges A has, it's going to be based on how many items are in this linked list. And why I'm writing a lot of degree vertex here for the adjacency list is because with the matrix, we're allocating things, we're allocating all the space early and squared, but then a lot of the operations are quite fast. I guess they're independent of I guess the structure of the graph. Whereas in an adjacency list, if we've got a graph that is really well connected versus a graph that isn't, this graph here, all the degrees are very small, so it's going to be really fast. Whereas with this graph here, when every vertex is connected to n minus one other vertices, all of these are going to be are going to approach n. So the adjacency list really, the efficiency is really dependent on how dense or sparse the graph is, so how well connected the graph is. So the matrix has pretty quick lookup, and its efficiency is independent of how well connected the graph is, but it is quite expensive in terms of memory. The list is again, if the graph is both memory and speed is very dependent on how well connected the graph is. If it's not very well connected, we're not going to have to allocate very many nodes, so it'll be very it won't require very much memory at all. And if it's not very well connected, all of these will be basically O of 1, because we're only ever going to have to visit like one or two other nodes in our linked list. But on the other hand, if it's well connected, these are basically going to be the same. If these are connected to n minus one other nodes each time, then it's basically going to take O of n squared memory, and all of these are going to take O of n to complete. So that's why some of these decisions might be made based on, if you have information about how well connected the graph is going to be, you might choose one over the other. Does that make sense? Any questions about this? 15 minutes. This would essentially, this would point to the head of the list, and this would be the head, the first item, like the BAAC would be the head. And I guess if we want a tail, it would just obviously just be the last item as well. Essentially, we'd have this vertex list, and each one of these would hold a pointer to the head of the list of I guess other vertexes that it's connected to. Yeah, so this is just a pointer. I guess this points to the front or the first node of the list, and if this wasn't connected to anything, it would just point to null. There would be no linked list associated, because head is kind of just null. That would just mean it has no neighbors, or it might just point to a list that the head, it might still point to an allocated linked list, but that has no elements. Any questions? Well, it is. It's the same as here, right? It's O of n plus m. You're going to have to, if you want to remove one of these, you might have to actually redo the whole array and the associated linked list. Because you're going to have to remove that from all of the other linked lists. You're going to have to actually go through, create a new whole array with one less spot, and then go through and redo all these. So it's essentially just going to be the whole thing, restructuring the whole list or matrix. Does that make sense? Any last questions? So I do want to make sure we can at least get part of the way through this. I think in 10 minutes we hopefully can. Any last questions? Can I go a bit bigger here? I think I can. So we're starting from A. Maybe I'll just keep track of the fact that we're starting at A, because that's above the screen. So again, I've got this DFS algorithm here, where we're going to be starting at a vertex, so A, so I've marked this as visited. And then I've got these two things for if we want to do a pre-order or post-order traversal, and we're actually going to explore this on the right side in a second. But again, what we're doing is we're saying for each neighbor of this vertex, so again, I've got two different neighbors here. What I'm going to do is I'm going to loop through the first neighbor first, so B, and then I'm going to say, if this hasn't been visited yet, then call the recursion on B. So I'm going to come in here, and now my vertex, the first time I called this, I was looking at A. Now I'm going to be calling this with B, and I'm going to do the same thing, mark B as visited, and then look at its different neighbors. And if its neighbor's unvisited, I'm going to call the recursion on its neighbor, which is going to be C. So what we're going to do is we're going to trace through this algorithm a little bit. I guess before doing that, though, I'll talk a little bit about the efficiency of it. So the idea here is that we're always going to call the recursion on a node if it hasn't been visited yet. So it's going to be called recursively on each vertex once. And again, what we're doing is we're also, again, going to label each edge as a discovery edge or a back edge. So again, we're going to look at every edge at least once as well. So with that in mind, again, the total number of things we're going to be doing on this is really just, we're looking at all n vertices plus m edges. So that's why, again, this algorithm is considered O of n plus m, which, again, same as before. N is the number of vertices, m is the number of edges. The discovery edges are just, I guess, if we want to create a spanning tree at the end, the discovery edges are part of the spanning tree. The back edges are edges that are removed from that spanning tree. Yeah. So let's actually keep track of when we visit an edge or a vertex in the pre-order and the post-order. So again, if I'm starting at A, I'm going to mark it as visited, which I'm going to do by coloring it red, and then visit it in the pre-order. So I'm going to visit A right away. Now I'm going to say, let's go through the first of A's neighbors. And I'll just do this alphabetically. So I'll visit B first. So I'm going to say, call the DFS, and now I'm on B. And I'm going to mark B as visited and visit it in our pre-order. And now I'm going to say now, and this is the discovery edge I've taken. And now I'm going to say, let's go through each neighbor of B's and see if it has not already been visited. So C has not already been visited. So I'm going to call DFS recursion on So it was on B, now I'm calling it, and my V is C. And I'm going to mark it as visited. And for C's neighbor D, I'm going to call the recursion on that and mark it as visited. And D's neighbor, I can choose G or H. I'll go to G because it comes alphabetically first. And I'll go and visit G. So again, I've called the recursion multiple times, but I've never actually got out of this loop. I've never actually got out of a recursion yet and done any post-order visits yet. I'm only going to do that once I've finished visiting all of a given vertex's neighbors. Well, we're going to see what the difference of pre-order and post-order is. Again, pre-order is every time you first see a vertex, you're visiting it. Whereas post-order we'll see is we're keeping track of the order of vertices I'm finished with. So I've completely exhausted all their neighbors, and I'm done looking at this vertex, and I've finished kind of processing it or whatever. So pre is kind of like the first time I see it, whereas post is keeping track of the order we finished the processing. So now at G, what I try and do is I would try and do the first, alphabetically, I'd try and visit B first, but that is where I'd get my first back edge. So I think why I created this is so I could kind of keep doing them step by step. So I'll say that we went to our first back edge this first time. And now what's going to happen is, so now for G, what I did is I went through the for loop. My current vertex is G. I said, let's go through each neighbor. If N has not already been visited, but in this case, B has been visited. So I'm not going to go into this if statement. I'm going to go into the else. So what I did is I labeled this edge BG as a back edge. I didn't call the recursion on B. So what I'm going to do is now I've finished this one iteration of the for loop. So I'm going to go back up, and I'm going to go to G's next neighbor, which would be K. And here I'm saying, it has N already been visited? No. Okay. Label this as a discovery edge and call the recursion on that new node. So now we've seen the first case where we actually, oh, sorry, and I'm coloring this new one now, where we actually made it through one iteration of that for loop. And now again with K, I haven't visited before, so I'm going to do this. I'm going to say for each of its neighbors, if it's not visited, print this as a discovery edge and go call the recursion on it. Same thing, it's just not visited, call the recursion on it. So what we're going to do is we're going to get to L, and again, the first neighbor alphabetically I try and visit from L is the G, and we're going to see, wait, this is visited. So again, now we're in our second iteration of the neighbors of L. The second node I might visit, so I guess I'll go to the next one now. Every time I do a back edge, I'll come to a new one. So now we're back at L. No, we still haven't exited the loop from any of them yet. We're in L, and we always call the recursion, so we never have finished the loop. We're in L. We've now gone through its first neighbor. We've looped back up once, but again, L has three neighbors here. So what's going to happen is we're now going to do, okay, now let's try its next neighbor, which is H here. And from H, we're going to visit it. Oh, I haven't been writing my things. We then visited K and O and then L, and now we're at H. L, we're going to see we've got another back edge. So now that when we're actually now in H, we've called the recursion on H. For H, we're saying go through each of H's edges, and we see that it's only got one neighbor that again there's no new neighbors for H. So we go through each of its neighbors, and it's got no neighbors that aren't actually visited. So we're never going to call the recursion again on H. We're actually going to label this as a back edge and then break out of the loop. So now that we're breaking out of the loop on H, we're then going to say we've visited, H is the first node that we've actually finished the recursive and got out of this algorithm and come back to the previous recursive call. So we called DFS on H. We called DFS on the neighbor H when from vertex L. So again, when we were in L, we said, try and go to G. It was a back edge. Try and go to H. And now we're done with H. So we've come back out of the recursion. We're going to keep going through the loop. So we've been through we've been through neighbors G and H, but now we've still got to do our last neighbor L. So we're going to call the recursion we still got to do the last recursion on P, not L. So we still have to do our last recursion on P. But what I'll do here is I'll denote the fact that we finished H. So maybe I'll do a new color, green here, which represents the fact that we're done processing H. So now I'm back in L, and we're going to now go down. So we finished H. We've got back edges here, and we're going to go down to P. So now we're going to call the recursion on P. And again, for P, we're going to say, do I have any unvisited neighbors? No, it doesn't. So what's going to happen? And you can do this all in one graph if you want. I thought that maybe breaking it out for people studying later might be better to see the kind of the process I followed here. So now what's going to happen is, because we have no unvisited neighbors so for P's for loop here, we're going to say, let's go through this whole loop. I've got no unvisited neighbors, so I'm going to get out of the loop at P and say I'm going to visit P in my post order. So now we've also finished with P as well. Because we call DFS, we call it recursively. So we from node L, we called DFS on H or we tried to go up to G, but it was already visited, so that was a back edge. Then we called H recursively. So we called DFS with H. When H finished, we're back out at the recursive call. Again, whenever we call a method, when we finish with running that method, we come back to where we made that method call. So now we're back here from node L, and then we called it with P. And then when we're in this recursive algorithm with P, what's going to happen is we're going to say go through each of its unvisited neighbors. It doesn't have any, so we're going to visit P in the post order and then end. So we're going to come back to the call on vertex L when we've now gone through the loop of L's neighbors, and we've said this was a back edge. We finished this recursive call, and we finished this recursive call. And now from L, we've finished we've checked all the different neighbors. Does that make sense, Jacob? So now, once we finish the loop at vertex L, now we're going to visit L in our post order and unwind. So we finished H, we finished P, and now we've also finished L. So now we're going to keep unwinding this way until we find a node with unvisited vertices. So what's going to happen is we're going to then be finished with L. So we're going to visit L in our post order, then we're going to be finished with O. So we're going to visit O in our post order, then we're going to be finished with K, then G, then D, then C, and we're going to get all the way back to B. Does this make sense? So again, we've realized that we've finished the for loop, and therefore the method for each of these other nodes. So we're just unwinding the recursion back to the last method. So now we're back in B. So the node we're at is B, and we just went through its first neighbor. We just finished going through its first neighbor, C, and now we'll see that G has already been labeled a back edge, so I'm not going to go there. And now we've got a new unvisited neighbor, F, so we're going to go down to F. I'm not sure what you're asking, Jacob. That's how recursion works. Again, when we finish a recursive call, we come back to the previous the recursive call that called that. From when we are in this algorithm and our v value is B, we called recursion on C, which caused us to go down that whole other tree. Now we're back from C. That's why I've colored C green. Now I've noticed that, oh wait, G's a back edge, so I'm not going to do that. But now we'll see that my next neighbor, which is F, is unvisited. So I'm going to call the recursion on F. And now we're going to be in DFS, but our node is going to be F. And now in F, we're going to go through all of F's neighbors. So we're going to go down here and go through all of F's neighbors and label them one at a time. Or I guess we'll go down to this back edge. So what we've done is we've now visited F, F, then F, then E, then I, then J here. Oh, I missed the back edge, but and we've colored all these ones green because we've finished with them. Yeah, exactly. But yeah, so sorry, I missed the one in F. When we got down to F, we would try and go up to A, and we'd see that A's already been visited. So we would just color this as a back edge. Yeah, exactly. Essentially, we're just saying, as we look at a neighbor, if it isn't visited, then we're going to call recursion on it. Otherwise, we're just going to make sure that that's labeled as a back edge. It depends. Sometimes what we'll in class tomorrow, we'll actually do something with back edges. For now, it's just, for now, I guess we could we don't really need this. I'm just drawing it to make sure, but we aren't going to actually do anything with our back edges. So you don't actually need the else here if you don't want. And what would happen is all these edges I'm coloring blue would just kind of be ignored in our traversal. But you might want to keep track of them just because they pretty much every time we see a back edge, that really means we found a cycle. So sometimes you actually do want to keep track of them. So now what we'll see is we're finished with, maybe I'll just color the new stuff. So everything on the right side of the graph is, we're finished with J. So then we're going to go down and do the same thing with M and N. So what's going to happen is we're done with J, we're going to do M and N. And now in our pre-order, we visited everything. What's going to happen is we're then going to be, finished with M next. Then we're going to be finished with M next. And then we'll go down to N. And then we'll be finished with N. So I'm trying to speed this up a little bit because of time. So what's going to happen in our post-order traversal is the next one we're going to be finished with after C is actually going to be J, then M, then N. And then as we back up, once we've finished these three, we're going to be finished with I, because we've now visited all of I's neighbors. So then we're going to be done with I. Then we're going to be done with, then we've finished all of E's neighbors. So we're going to be done with E. Then we've done all of F's neighbors. So we're going to be done with F. Then we're finally done all of B's neighbors. And then finally at the very end, we're done with A. So we're going to, again, unwind. So our post order, again, keeps track of when we finished processing that vertex, and we started unwinding in our recursion. Whereas our pre-order is, okay, this is the first time we ever saw any of these vertices. So again, depending on what type of problem you're modeling, what type of problem you're trying to solve, sometimes again you want to know, okay, I'm done with this part of the tree, I'm unwinding, or I know that this didn't lead to a valid solution, or it did find a valid solution, or it found one of the possible valid solutions. You might want to do a post order when you're kind of finished the handling of something. Whereas if you're just trying to do an exploration and see, okay, when's the first time I've actually seen something, you might do a pre-order. So again, both these traversals are used for different types of things, but I guess from the default binary breadth first search, the idea is, depending on what type of problem you're solving, you can also often, if you're looking for something for the first time, you can just say, hey, when I first get here, let's do it. Otherwise, if you want to only kind of process something after you finish going to all the other options, all of its neighbors, then you would say, kind of record that you're finished with it at the end of this method. So again, two different kind of just really quick and easy things to add to a DFS traversal that allow you to get a lot more information about the structure of the graph. Does that kind of make sense?